red bulbs, R1, R2, R3, R4, R5 and R6. If you have them like this, if you can distinguish between these 6 red bulbs, then R1, R2, R3, this combination of red bulbs will be a different one than this one, R5, R6 say, or for example R1, R5, R4 will be a different combination. So that's why the number is this. However, if they cannot be distinguished, they are just some indistinguishable red bulbs, then no matter which 3 you choose, you get the same combination, only one. So in that case, this will be the number. But I don't think they meant identical balls. Okay, whenever a question is given to you which asks you about the number of ways of choosing, most of the time it's assumed tacitly that the objects involved are distinguishable or distinct. This is the case that we considered in permutations in the first part of the permutations. First we considered permutations of distinct objects, and then we considered permutations of objects where they are not necessarily distinct. Okay, so distinctness is tacitly assumed because this looks quite weird. I mean, this will not be asked, but whatever be the case, you try to understand what the question says, and if nothing else is said, then you should assume that the objects are distinct. Okay, so assuming distinctness, this is the answer. Then the next one, in how many ways can we form a group of, again a card problem. In how many ways can we form a group of five cards? A group of 5 cards out of 52 playing cards, that's understood, so that the group contains exactly one ace. Okay. Okay, now it's not 4 cards. Okay, we have to choose 5 cards from a pack of 52 playing cards, but the group that we are choosing of 5 cards, each such group should contain exactly one ace. There are 4 aces, ace of each symbol, right? Ace of hearts, ace of diamond, etc. So there are 5 things we have to choose, but there should be exactly one ace. Now since there has to be exactly one ace, so the aces have to be considered separately, right? So from 52 cards, we have 4 aces, and 52 minus 4, which is 48 non-aces. So one ace has to be chosen from these 4 aces, and that can be done in 4C1 ways. And the remaining 4 cards, okay, one card has been chosen and that is an ace. the remaining 4 cards have to be chosen from this remaining 48 non-aces, because the group must contain exactly one ace, not more, not less. So 48C4, and they together form the group. So we multiply. So in these many ways we can choose 5 cards out of 52 playing cards so that the choice contains exactly one ace. Okay, so this is the answer. Although I am writing one-line answers, but the solutions have to be elaborate. I mean, we should write all the things that we need to write, okay, which I am not discussing. You know very well how to write a solution. You have to say all the things that the number of ways of choosing. First of all, you will say there are 4 aces and 48 cards which are not aces. Then the number of ways of choosing one ace from 4 aces is 4C1, and the number of ways of choosing 4 cards which are non-aces is 48C4. Hence, the total number of choices of 5 cards where exactly one ace is there is equal to this. So these things have to be written in the solution. So we go to the next question. Among 17 cricket players, cricket players, there are 5 bowlers. In how many ways can we form a team of 11 players having exactly 4 bowlers? Okay, so there are 17 cricket players. Out of them, 5 are bowlers. Now we have to make a team of 11 players, and they should contain exactly 4 bowlers. So the number of bowlers is 5, and the number of non-bowlers is 17 minus 5, which is 12. Okay. So from these available people, we have to find a team of, we have to form a team of 11 players, but there should be exactly 4 bowlers. So 4 people can be chosen from 5 bowlers in 5C4 ways. And how many more people do we need to make a team of 11 people? 7 people, right? And they have to be chosen from the non-bowlers. So that can be done in this many ways, and they together make the team. So that's why we multiply. This is the answer. Okay, so 2 more questions are left. How many groups of letters how many groups of letters with 3 vowels and 2 consonants can be formed with the letters of the word involute. Involute is a word, I think it is related to the subject of botany, so far I remember. It has something to do with arrangements of petals or something. I don't remember correctly, but that's the thing. Okay, so here we have the letters of this word have to be chosen, but not all. We have to choose 5 letters at a time. 3 have to be vowels and 2 have to be consonants. So we single out the vowels and consonants separately. I, O, U and E. These are the vowels. And the consonants are the remaining ones N, V, L and T. So there are 4 vowels and 4 consonants. So our choice should contain 3 vowels. So the vowels can be chosen in 4C 3 ways. And the consonants can be chosen in, since there are 2 consonants, 4C 2 ways. So the total number of ways of choosing this, so that there are 3 vowels and 2 consonants, is this. And finally, there is this question. Let me write it here because it has parts, just like the one that we have seen some time back. This also has parts. From among 3 girls and 7 boys, 3 girls and 7 boys, in how many ways can a group of 5 be formed such that part A, the group contains no girl. Okay, part B, the group contains at least 1 boy and at least 1 girl. At least 1 boy and at least 1 girl. And part C, the group contains at least 3 girls. Okay, so as the parts are progressing, you can see, first of all, there is no girl and then there should be at least one girl and then at least three girls. So the level of misogyny is decreasing. Okay, the first group is extremely misogynist, it's against girls. Then the second group allows at least one girl, and the third group allows at least three girls. So we start the solution. Contains no girls. How many have to be chosen? 5. Right, so 5 people have to be chosen. So all of them have to be boys. So 7 C 5. If you want, you can choose 0 girls from 3 girls. It can be done in 3C0 ways, and you multiply. That can be done, okay. But it will not matter because 3C0 turns out to be equal to 1. You can calculate and see that this becomes 1. So if you write it or you don't write it, it does not matter. So in these many groups will have all boys. And this is actually, we can find the value. You see, if you go back to the, what to say? Okay, let's just forget about this. Let's find the value. To make things simple, if you recall this formula, NCR equals NC n minus R. I have already said that when these numbers are somewhat close but large, although here they are not large, but nevertheless they are somewhat close. So 7C5 can be written as 7C7 minus 5. So this is 7C2, and your job becomes slightly easier. So it's 7 factorial divided by 7 minus 2 means 5 factorial times 2 factorial. So this is 7 times 6 times 5 factorial, 5 factorial into 2. So these two cancel out and we are left with 7 times 6 divided by 2. Let me tell you about a trick here. Whenever you see NCR, right, what you do, NCR, you write in the numerator, you write R factors, starting from n and then decreasing them one by one. Here, for example, I have 7C2. So in the end, I will have 2 factors in the numerator, 7 and 6. In the denominator, you write the factorial of R. That is, you write like this, n minus 1, etc. up to n minus R plus 1 divided by R factorial. Do you know, can you guess why this is correct? Why this formula is like this? It's because if you recall, this part, the numerator is nothing but NPR. And we already know that NCR is equal to NPR divided by R factorial. So that's what we are using here. So instead of doing these calculations every time writing factorials and such, you can just simply write the factors in the numerator, how many of them are R number of them. So here we have 2, so we write 2 factors starting from 7 and then decreasing one by one. 7 times 6 divided by 2 factorial. 2 factorial is 2. So this gives you 7 times 3, which is 21. So there will be 21 groups of 5 boys, all of them boys. Then the next one, okay, here we will have cases. The group contains at least one boy and at least one girl. Now there will be cases because it may contain more than one boy and more than one girl at the same time. Okay, so there should be 5 people. So let me write like this. One girl, exactly one girl. Okay, so then 4 boys have to be there. Okay, then you increase the number of girls. 2 girls, then here the number of boys will decrease. 3 girls, 2 boys. 4 girls, 1 boy. But you cannot go any further than this, because if you have 5 girls, then there will be no boy, and that is not allowed. It should also have, the group should also have at least 1 boy. Okay, besides having at least 1 girl. So the number of ways of choosing this combination is 1 girl, right? So there are 3 girls. So 3C1 times 4 boys out of 7. 7C4. Here the number of combinations is 3C2 times 7C3. Here it is 3C3. Oh, I made a mistake. 3C3 times, okay, let me write this one. 3C3 times 7C2. I wrote 4 girls, but 4 girls are not available. So we will go till this only we can go. Okay, 4 girls does not make sense since there are 3 girls only. And these are cases, separate cases, because here 4 plus 1, 5 people have already been chosen. The group has been formed. Here also 2 plus 3, 5 people, 3 plus 2, 5 people. So they have to be added up. 3C1 times 7C4 plus 3C2 times 7C3 plus 3C3 times 7C2. So this is the answer to the part B. So in these many groups, we will have at least 1 boy and at least 1 girl. Then in part C, finally, the group contains at least 3 girls. Now since there are 3 girls available, so they have to be chosen. Okay, so there has to be 3 girls at least, but since there are at most 3 girls, so there should be exactly 3 girls. So 3 girls and 2 boys, right? Yes, 2 boys, and this we already know, 3C3 times 7C2. So 3C3 is 1 and 7C2 we already have found out there. So 21. In 21 groups we will have all the girls. And that's all about combinations. I mean the ones that I wanted to show. There are many more problems that can be solved. So the more involved and complicated ones, which are somewhat unusual, we will solve them and see them another time. Okay, so with this I end this video and this series of videos known as permutations and combinations. If you enjoy the videos, please make sure to subscribe to my channel. It helps me out a lot. And so that's all for this series. After this I am planning to go to binomial theorem, and after that we will study some elementary probability theory. Since these two things are where we use these ideas of permutations and combinations. In binomial theorem we use combinations mainly, But in elementary probability, where the number of possible outcomes is finite, in that case, we use permutations, combinations sometimes. So with that, this is all about these theories. So it's me, the caretaker, signing off from this mathematical room. Have a nice night.